Observe shifting share prices, consumer buying habits, or corporate turnaround strategies in the wild, and you are looking at raw business phenomena. In their natural state, these events are unstructured noise. They are too messy, too broad, and too chaotic to be studied directly. To evaluate these phenomena with any actual precision, you have to force that chaotic reality through a strict architectural funnel. You have to convert an observation into a researchable problem. This conversion follows a rigid sequence. You start with a broad problem statement, narrow it to a precise research question, and isolate your specific unit of analysis. From there, you construct a theoretical framework of interconnected variables, which finally outputs testable hypotheses. We are going to blueprint this exact process. We will extract a conceptual model from existing literature and define the precise mechanical roles that individual variables play within it. Without this structural conversion, empirical research comes to a halt. You cannot mathematically test a vague idea. The process begins by translating a broad business problem into an open-ended explanatory question. This means moving past simple yes or no inquiries and framing the problem around to what extent or how something occurs. The foundation of this question relies on one strict parameter, the unit of analysis. This is the exact entity, the specific subject that the researcher intends to draw conclusions about. Data exists across different levels of aggregation. We can look at highly aggregated data at the top, like entire countries or geographical units. Moving down, we hit medium aggregation, observing groups, firms, or boards of directors. At the base, we have low aggregation, the most granular level, focusing on individual CEOs, investors, or consumers. The specific tier you select is the perimeter of your study. It determines exactly what kind of conclusions you are mathematically allowed to draw. Ignore this perimeter, and you invite the ecological fallacy. This is the error of observing high-level, aggregated data, like a country's economic output, and using it to draw specific conclusions about the individuals living within that country. The downward logic fails. The inverse is the atomistic fallacy. This occurs when a researcher takes granular, individual-level observations and scales them up to make sweeping claims about entire industries or groups. To lock in the correct unit of analysis, the study's background section must operate like a funnel. It begins by framing the broad context with concrete evidence, smoothly narrows down to the specific problem, and proves exactly why this narrow focus holds both academic and managerial relevance. If you select the wrong unit of analysis or commit a fallacy of aggregation, your logic collapses. The study is invalidated before data collection. With the problem defined and the unit of analysis secured, researchers turn to existing academic literature to find the raw materials for their framework. A standard literature review synthesizes past research to show what is already known and where the gaps lie, but a conceptual model goes further. It visually represents the architecture of the new proposed study. To build this model, we extract foundational building blocks from the literature. These blocks are called variables. A variable is precisely what its name implies, an entity capable of taking on varying values. Those values can fluctuate across time, across different objects, or across different people and situations. To function in a study, a variable must be given an informative, jargon-free name, and it must be anchored by a strict definition sourced directly from the literature. This is why purely descriptive questions, such as asking what percentage of companies pay dividends, are academically weak. They isolate a single variable in a vacuum and simply measure its size. Rigorous research demands more. It requires a question that connects multiple variables together, probing exactly how they relate to and influence one another. If you extract variables from literature without defining their relationships, you have compiled a list. You have not built a theoretical framework capable of generating new knowledge. The conceptual model is the mechanical blueprint of the study. It maps out exactly how these extracted variables are expected to interact. This formal schematic shows the three primary ways variables interact. At the top is the main effect. We have the independent variable, x, which is the factor expected to exert influence. It points directly to the dependent variable, y, which is the primary outcome the study wants to explain. Moving to the middle row, the architecture becomes more complex with mediation. Here, a mediator variable sits perfectly between x and y. It explains the hidden mechanism. If X causes Y, the mediator explains exactly how or why that outcome occurs. It is the connective tissue. In the bottom row, we see moderation. Notice the orthogonal line dropping down to intersect the main pathway. A moderator variable does not explain why something happens, it dictates when. It represents an external condition that changes the strength or the direction of the relationship between X and Y. It can amplify an effect, weaken it, or reverse it entirely. Finally, outside of these direct pathways, researchers introduce control variables. These are essential background constraints factored into the math to rule out competing alternative explanations for the outcome. This visual model acts as a mathematical blueprint, dictating the specific statistical tests the researcher must execute to validate the study. The final step of this architectural phase requires translating the visual links of your conceptual model into formal, text-based statements. A hypothesis is a precise, unambiguous, and tentative statement defining the expected relationship between variables. A directional hypothesis makes a highly specific prediction. It charts a trajectory, stating that an increase in variable X will lead to a higher, lower, stronger, or weaker variable Y. Contrast this with a non-directional hypothesis. We use this when the literature confirms that a relationship definitely exists, but the existing theory isn't strong enough to confidently predict which direction it will swing. At the core of testing these statements lies the dichotomy between the alternative and the null hypothesis. The alternative hypothesis states that a relationship between the variables actively exists. This is what the researcher actually believes is true. The null hypothesis is the mathematical baseline. It assumes absolute zero, no relationship, no effect, no difference. The entire statistical apparatus of the study is set up strictly to reject this null baseline. Hypotheses serve as the final output tolerances of your study's design. If these statements lack precision, the conceptual model you just built cannot be empirically validated. We never start empirical research by looking at the data. We start by grounding a broad problem and locking in a specific unit of analysis to avoid the logical traps of aggregation. We extract variables from literature, construct a visual map calculating the exact mechanics of mediators and moderators, and we lock that framework down with highly precise, testable hypotheses. This sequence is exactly what separates casual observation from rigorous academic inquiry. By completing this process, the research methodology becomes a fully engineered mechanism. It is finally ready to accept and process raw data. The theoretical framework provides the structural integrity of the entire study. Without it, you are not performing research. You are simply collecting random facts.